So now we are at plenary session 2, and in this plenary session we have Professor Karen from the beautiful country Switzerland. We have Professor Thomas from the country who is leading in the automation and machinery, Germany. So before inviting our renowned speakers, two lines I remember that is written by George Bernard Shaw. Although he was not linked with the science, but he has written for the science. That is, science never solve a problem without creating 10 more problems. So you can see, like whenever we are concluding the research, we see the future scope of work, and this future scope is having more than 10 problems. So now it's my pleasure to invite Professor Karen on the dais, and have a big clap for her. She is Professor and Head, Laboratory of Construction Material, Department of Materials, Swiss Ecole, Polytechnique, Switzerland. Ma'am, please take your seat. Yeah, please. Now I would invite Professor Dr. Thomas. Please have a big clap for him. He is Chair of Building Materials, Institute of Building Materials Research, Aachen, RWTH, Aachen University, Germany. Sir, most welcome. Please take your seat. Now to chair the session, I would invite third professor of this dais, Professor Shashank Bishnoi sir from IIT Delhi. And now to represent NCB on dais, I would invite Dr. S.K. Chaturvedi, Joint Director, NCCBM. Now I request Dr. S.K. Chaturvedi ji, please present a bouquet to our chairman and speakers. Yes. Now I request Dr. S.K. Chaturvedi ji, please introduce our chairman and take this session forward.
Good morning and welcome to this plenary session. I have the honor and privilege to introduce Professor Dr. Shashank Bishnoi, Professor, Department of Civil Engineering, IIT Delhi. Yeah. He is BTech Civil from IIT Kanpur, Masters of Engineering from University of Tokyo, PhD from Institute of Materials, Ecole, EPFL, Lausanne. Completed more than 230 consultancy projects for over 130 clients, including Lausanne and Tubro, BHEL, RBI, CPWD, and so on. Authored more than 70 journals and 150 conference papers in leading international journals, contributed chapters in books, carbon emissions and their mitigation in the cement sector, and calcined clay for sustainable concrete. Expertise in numerical studies into hydration of cement and supplementary cementitious materials, sustainability, resource utilization, durability and repair and life cycle cost of concrete structures. Now, welcome Dr. Isri. I request now to please introduce chair and co-chair.
Thank you, Dr. Chaturvedi. It's a pleasure and honor to be here today. And to start with, I would like to introduce Professor Karen Scrivener. It's an honor for me to do this over here because Professor Karen Scrivener was my PhD supervisor. I've been working with her for quite a long time. She is the head and the director of the Laboratory of Construction Materials at Ecole Polytechnique Fédérale de Lausanne in Switzerland. She has a PhD from Imperial College London. More than 40 years of experience. She doesn't need any introduction to this community. Of course, she has been the chief editor of Cement and Concrete Research. She started a very successful research network called NanoCem, which converted into Innovandi, which is a global cement and concrete research network today. So whenever you look up any research work related to cement hydration, you'll always find the name of Professor Scrivener over there. And today we have we are fortunate to have Professor Karen Scrivener here to give the first talk. Professor Scrivener. Her talk is going to be about the role of cement hydration and decarbonizing cement-based materials. So I'll have to be very strict with the time, Karen, 40 minutes.
Okay, so thank you very much for the kind introduction. And today I'm going to talk about cement hydration, but also particularly about CSH, because Shashank said, you know, we want to give people more idea about cement chemistry, particularly as we will be back here again in just under 3 years' time for the Chemistry of Cement Conference in 2027. So I'm going to give you some perspectives of CSH, what we call CSH, and really linking the kind of fundamental science to the problems we're facing today, to show how understanding things at really a very quite deep scientific level can really then find application in the field. And the quote of the person who introduced this session from George Bernard Shaw is very appropriate because we've learned a lot in the last 40 years, but there's still a long way to go. So first, just to give a bit of perspective, we have to realize the overwhelming importance of materials based on cement, like concrete. These make up more than 3/4 of all materials produced. And from that perspective, the fact they account for something like 8% of CO2 emissions is actually relatively modest. And purely from an availability perspective, we cannot replace concrete by anything else, but we can make it a lot better. Now, in making it a lot better, we have to bear in mind how the use of cement has changed dramatically in the last 60-odd years and how it will change in the next 30 years. So you see, back in 1960, just shortly after I was born, we had nearly all the cement production in what we call the global north, Europe, USA, etc. And in the last 40 years, the huge change has been the development in China, which now accounts for more than 50% of cement use. But in the next 30 years to 2050, we're going to see a big change again, away from China and towards other developing regions, particularly India and Africa. Now, I think we know the origin of the CO2 emissions from Portland cement. Most of the emissions are coming from the breakdown of limestone. And this, of course, leads people to say, well, you know, can't we use something other than limestone? Now, I'm not going to go through why this doesn't work. You can see several of my presentations online which go into that in detail. But basically, all the alternatives are totally impractical, way too costly. For example, producing cement from algae or seawater would cost probably 10,000 times the cost of cement today. And they're unscalable or way long away from practicality. So we have to realize that cements based on Portland cement are an inevitable consequence of the chemistry and geology of the Earth. But that doesn't mean we don't have means to reduce the carbon impact. We have a lot of means to reduce impact. Here I basically show the 5 main ones. As we're going down, we're reducing CO2, and on the horizontal axis we have the cost. So you can see the ones at the top: efficiency in design and construction, efficiency in concrete production, and particularly savings in cement and binders, and of course alternative fuels, can all be introduced at even negative cost. And we really need to maximize what we can deliver with these levers, because there will always be some gap, and that will have to be filled by carbon capture and storage. But there we talk about a totally different order of magnitude of cost. Now, to understand why basic science is important, we need to understand how cement works. What we have this gray powder, we mix it with water, and at the beginning we have a fluid suspension. We have these cement grains floating around in water, and that gives us the possibility to transport the concrete and put it into the different forms. Now, inside the concrete, we have these chemical processes taking place. First of all, we have the dissolution of the cement grains. That's like sugar dissolving in your coffee. But once the cement grains have dissolved, once they put calcium and silicon ions in solution, those ions can make new combinations, and those new combinations precipitate as what we call hydrates. And these hydrates, because they incorporate water in their structure, they have a higher volume and they hold the grains together, creating a rigid solid. So this was a diagram, but if we look in the real structure, here we see cement grains. We see that they're polymineralic. They contain all these different phases we know, like alite, belite, ferrite, aluminate. And then after hydration, those grains have reacted. And what's particularly important is the filling of the space between the grains. And the main phases that fill the space between the grains, well, we have some calcium hydroxide, but most importantly, we have what we call this calcium silicate hydrate, this CSH. It's intermixed with some other phases, but about half the space is filled with calcium silicate hydrate. So what is CSH? Okay, this stands for calcium silicate hydrate. We can think of it as the glue of concrete. And if we think about it, it's actually the most abundant fabricated phase on Earth. We actually produce about 3 billion tons every year. So that means if we add up all the buildings in existence that haven't been demolished, we have maybe 50 billion tons of this material in existence. And when I started my PhD in 1980, the common view was this was just an amorphous goop. Now, fortunately, and it was people said it was an amorphous goop, but you could have some quite beautiful pictures. This is one picture I took during my PhD thesis. And you can see this kind of very attractive kind of needle and morphology. Sometimes people talk about it looking like a sea urchin. Now, what was already realized, particularly Hal Taylor was a pioneer in this field, was that there was a lot of similarities in basic chemistry between CSH and this natural mineral tobermorite. So tobermorite is the crystalline phase. This means we can well analyze the structure by X-ray diffraction. And you see the structure here. The most important characteristics are these layers of calcium and oxygen. On either side of these layers, we have these chains of silicate. And in between the layers, we have this interlayer water and calcium. So I'm not going to go into all the details because many people have contributed to this, and we really took advantage from the 1980s by the advent of NMR, nuclear magnetic resonance. Groups in France, Oxford, many places really little by little deciphered the structure of real calcium silicate hydrate. And in recent years, we've been able to contribute to this, notably by the work of Aslam Mohammed Kuni, who is now in IIT Madras. And we now know that CSH is actually a highly defected tobermorite. If we look at some of the differences between this structure here and the CSH, what we see is that a lot of the chains are broken up. They're not long continuous chains, they're broken up. And this is actually probably quite an important aspect when we then consider the growth. And if we can, now I don't know how I can play this, oh yeah, here. So this is now some TEM work we've done recently, where we can make a sample and then we can rotate it in the transmission electron microscope. And in doing that, you can see the structure. You can see how these layers that are in the atomic structure actually then make up these needles. And in cross-section, we can see that these needles, they are actually porous. These are actually the first images we have of the gel pores, which is a very important component because it gives the CSH more volume, it enables it to fill more space, it makes it stronger and more durable. So this CSH, for which we now know the detailed atomic structure, we now know how this atomic structure is arranged in real CSH. So you may say, well, what else do we need to know? Well, I think most importantly what we need to know, we need to understand this hydration kinetics. So we're often following the rate of reaction by looking at the heat evolution by calorimetry. And here we see the heat evolution over the first day or so. The first few hours, we have a period of low reaction, and this gives us the possibility to transport the concrete into site and place it in the forms. And then we have this main evolution, and the question is, well, why does this stop? Why by one day do we start to have a low rate of reaction? And this is quite important because the fact we have this slowdown at one day is a big limitation on the amount of clinker which can be substituted, which is the technology which has the most potential to reduce CO2. So here, for example, you see strength development for mixtures with calcined clay, with slag, and with fly ash. You see that at 180 days, all these mixtures have very good strength, higher than the reference Portland cement, but the problem is the relatively low strength at 1 day and even for fly ash at 28 days. And this means that, this is one reason why the clinker substitution has not evolved over the past few years. Of course, the other reason is very much the limitation in the availability of slag and of fly ash we have. So we've been using slag and fly ash, but in fact the amounts of these two materials is only today about 15% of the amount of cement produced and will decline in the future as hopefully we move away from coal. Now, this is why we started the work on calcined clay. With calcined clay, we can remove this limitation in supply of SEMs, and I think today we could easily go to a substitution level of about 40%, 60% clinker factor. This would represent a saving of about 400 million tons of CO2. But if we could also manage this low early strength problem, I think we could do twice as well as that. We could really go to substitution levels of around 45, 50%, and this would represent 800 million tons of CO2 saved. That's like 20% of the emissions of India, like 20 times the emissions of Switzerland. So, you know, it's a huge contribution to CO2 reduction. But in order to get there, we need to solve this problem of low Hurley strength and the main hydration peak. So we spent a lot of time looking at this. I mean, this started with the thesis of Shashank 20-odd years ago. We know very well what's happening during this peak. We know that we have the growth of this CSH phase. It grows mainly on the surface of the grains. And for a long time, people had put forward hypotheses for why we had this slowdown. The most popular hypothesis was that we form a layer of hydrates, and then we had diffusion control, and the other hypothesis was that we had impingement of product. Well, in fact, what we found out with the modeling work of Shashank is that neither of these hypotheses by any means fit the experimental data. So if we look first of all at the diffusion theory, the idea is that we have this continuous layer and either calcium silicate or water have to move through this layer. And here we can see that it appears to fit very well the data. But in fact, because we had this wide range of particle sizes, exactly the same A-light, but fractionated into these different particle sizes, we could see that the fits could only be obtained if we arbitrarily varied the diffusion coefficient by 10 times. And that makes absolutely no sense, because we're talking about calcium silicate hydrate, which is always formed through solution, so it's exactly the same in all those cases. It can't possibly have a diffusion coefficient which varies by an order of magnitude. And there's actually a lot of other evidence against that diffusion hypothesis. Perhaps the most damning of all is the fact that we actually don't have a continuous layer at the peak. Here you can see a picture of C3S taken at the peak, and you see there's no continuous layer in that red circle. You can still see the surface of the A-light gray. So diffusion is not the reason for this slowdown. The second reason that had been proposed by many people came from the so-called Avrami equations. And Avrami developed these equations for solidifying metals. And the basic idea is you have these first nuclei, these green particles, and the rate of growth is proportional to their surface area. So first of all, the particles get bigger, and therefore the growth rate goes up, and then they start to impinge on each other, and the growth rate goes down. So these equations give you these kind of curves, which look like a cement hydration curve, and back in the 1970s already, people like Tenutas were trying to model cement hydration with the Avrami equation. But the problem is you get different values for the parameters for every cement you study, which again makes no sense, because what Avrami had shown was that the parameters in the equation are really related to physical entities. And you can see here that you put this in a model that we just do not capture the deceleration because there's nowhere near enough product to start impinging. And perhaps the most problematic evidence of all was the finding that the amount of hydration was really quite little impacted by the amount of water-cement ratio. So as you increase water-cement ratio, the grains should be further apart, so you should be able to have a lot more hydration. But this is not seen. And I then had another student, Amélie Bazzoni, who very carefully made measurements in the TEM and found that if you looked at the length of these CSH needles, they grew very fast, and then their rate of growth slowed down very dramatically. It doesn't stop, but it slows down. And we can change this by actually putting low concentrations of zinc into the alites. You see here, this is quite dramatic. You see there's a very big change between the control black curve and the red curve, which contains a low concentration of zinc. And this could be, quite a breakthrough, because the strength results on the right show you that even though these two mixtures have the same strength at 28 days, at 1 day, the strength with the zinc mixture is about 3 times higher. This seems really great. So we then tried to see if this would work in clinker, and unfortunately it doesn't, because you can't keep the zinc in the alite phase. It goes into all the interstitial phases, the aluminate and the ferrite. So that's a bit of a problem. But nevertheless, this influence of zinc really gives us a very good idea of what could be going on. We can see this really dramatic change in the CSH morphology depending on the amount of zinc, and I'll come back to this in a second. So then we come up with a new hypothesis based on this growth of the needles to a certain length and then slowing down. We integrated this in a model in the thesis of Uzia, and now without any fitting, these parameters are all taken from experiment. There's no fitting parameters. We could correctly model the evolution in many different cases with many different particle sizes. So the hypothesis, what we could show is the hypothesis that have been around for years are really incorrect. It's not diffusion through a layer. It's not an impingement of products. And it underlines the importance to look at a wide range of variables and have physically measurable parameters. And the best hypothesis we come up with is we have fast growth of needles to a critical length. So, now we want to say, well, okay, if this is what's happening, what controls this? Is it the changes in the solution concentration? These are quite difficult to measure with a very fine time resolution. Or is it just simply because this CSH, you can see the foils, they're not flat, they're kind of curved. And is there a kind of phenomenon that after a certain point, the foils become so distorted, they have problems to grow fast? So these are still the open questions which we're still trying to look at. We went back to the question of zinc, and we have this very nice paper with a big team contributing to this paper. And by using this rather sophisticated what's called DNP NMR technique, we're fortunate to have a colleague professor at EPFL who is really the world expert in this. We could start to decipher where zinc was in the structure. And what we could see is that the zinc is actually going into these silicate chains, and it's helping to make these silicate chains longer. So it may be that the growth of those silicate chains is what's controlling the growth of the CSH phase. And that's what we're trying to look into now. We have 2 new PhDs starting, where we want to look into CSH growth in more detail, try to find the controlling factors. We know that zinc can influence it, but maybe there are other things, other admixtures that can influence that. And that would allow us to have a faster rate of strength development, to more optimize our clinker, and also then to go to higher levels of clinker substitution. So the second part, which I just want to touch on briefly, is to highlight that the role of CSH doesn't stop with the hydration and strength development. It's also very critical in looking at, in understanding the transport and durability. And particularly we realized this when we looked into these same blends which I showed you earlier. So these are kind of binary blends, either with clinker and either calcined clay or slag or fly ash, or the same mixtures also with limestone. And what we see, if we look at the chloride ingress, so this is simply, we put the samples into a solution which has about the same chloride concentration as seawater, and you can see the dramatic improvement made by the supplementary cementitious materials. So the black line is the ingress in the reference Portland cement. The red curves are with slag, you can see it's a lot better. The blue curves are with fly ash, you see it's better again, and the purple curves, last of all, with calcined clay, which are best of all. And you can calculate the apparent diffusion coefficients, and you can see that the calcined clay mixtures have diffusion coefficients about 10 times less than the reference. Now, why is this? Well, a lot of people said it's due to the pore structure. So we looked at the pore structure, we looked at the kind of measures of the connectivity, like the breakthrough diameter in MIP, and basically we see there's no obvious relationship. All the systems have pore structures which are very similar. So then everybody said, well, it's binding. So we did the binding experiment, and there are some differences, but in the range of concentrations that are of concern, the kind of concentrations we have in seawater, we see that most of these things don't vary that much, and where we do have variations, these do not correlate with the amount of ingress. So here we see the dependence of the chloride penetration depth against the bound chloride, and again you see there's really no relationship. So what is it? Well, we then kind of had some indications that it was related to the pore solution, and the pore solution itself is very critical in determining the composition of the CSH. So here we see that very small changes in the alkalinity can make very big differences in the diffusion coefficient. And I want to underline that even at this sodium-potassium concentration of 100 millimolars, you still have a pH of about 13, so you're still protecting your reinforcement. What we also see is we see that there's a systematic change in the composition of the calcium silicate hydrate between the OPC systems on the left and the systems with additions either of slag, either of fly ash, silica fume. I don't have the calcined clay data on here, but this also shows its change. So this gives us a hint that the pore solution changes, the composition of the CSH changes, and this affects it. Now, to understand this, we just have to really understand a bit better what's happening in a real cement paste. We have this phenomenon we call chemical shrinkage, where the volume of hydrates is lower, and this means that in all concretes, even ones nominally cured underwater, we create voids, and we have a lowering of the relative humidity. And this lowering of the relative humidity means that the pores, which still contain solution, the pores which contribute to the transport, are actually very small. And after a few months, we're really talking about solution only being in pores of around 10 nanometers or so. So what are these pores 10 nanometers or so? These are basically the channels between this CSH needle. These are also the gel pores, these very small pores, as we see in these TEM tomographic images. And really look at the comparative size between the sheets of the CSH in yellow there and the pores in black. The pores are about the same size as the thickness of the CSH sheets. And then we go into atomistic modeling and we look at what a sheet of CSH may be. So here we see a sheet of CSH. It's got about 3 of these calcium layers. It's got then 2 interlayers, but each surface, you see there's a very diffuse arrangement of the calcium ions, drawn here in blue, on the surface. And that surface-affected layer is actually quite significantly large compared to the thickness of this CSH sheet. And it's that complex surface structure which is actually then directly affecting the transport of chloride ions. And as we change the calcium to silicon ratio of the CSH, we will change the surface structure, and that directly affects the mobility of chloride through the structure. So it's not due to binding, it's not due to a more connected or less connected pore structure, it's due to the surface structure of the CSH, which is incredibly important because it just makes up the surface of nearly all the pores. So, what I hope to have communicated to you is that, in the 40 years I've been in the field, we've seen tremendous progress in understanding CSH. We realize it's not just some amorphous random goop, but it is a well-controlled phase whose composition depends on the pore solution of the cement. But there are still many critical points where we need to go further. We need this really quite fundamental research, bringing in techniques like DNP, NMR, atomistic modeling, where we need to go further to, first of all, understand, but then to generate ideas where we can progress. So we see that the CSH growth limits the early reaction of clinker, and so is really linked to the levels of substitution we can go to. If we can come up with admixtures to remove these limitations, we can go to higher levels of substitution, and we can reduce CO2 impact. And then we have the CSH surface structure, which is very important to understanding durability and predicting how things will change in the long term. So with that, I'd like to thank you for your attention and looking forward to answering any questions. Thank you.
Thank you, Professor Scrivener, for the very informative presentation. I hope the audience enjoyed and got a lot of information from this. Let's have a few questions. We have time for them.
There's one right at the back.
Professor Singh.
Thank you, Professor Karen. This is one of the best lectures I heard on CSH. My just question is, you mentioned that if you add zinc, so please correct me if I'm wrong, it polymerizes the CSH gel. So other than zinc, can I take something else that will also polymerize?
Well, that's the big question.
Okay.
That's what we're looking at.
And when you took zinc, is it in a powder form maybe?
No, you have to, because if you have high concentrations of zinc, like if you add a powder, this would give you massive retardation.
Okay.
So you have to have very low concentrations of zinc, so they don't give too much retardation, but they also go into solution the same time as halide. So we're now looking at 2 possible routes. One route is how we keep more zinc in the halide from a practical production point of view. But the other route is to think, well, are there other things that have the same effect that could be added like as an admixture, like a superplasticizer or something like that? And I think both these approaches have quite a good possibility of giving us something in a few years' time.
So how you got the idea to take zinc only?
Sorry?
Why you took zinc only?
Well, it was kind of coincidence. We kind of had this collaboration with Nanjing University of Science and Technology, and they'd done several solid solutions. They'd looked at magnesium, various other things, and zinc. And just by coincidence, we found that zinc had this massive effect. And if you could, if you could do this in a real clinker, it's not so impractical because you've got very low concentrations of zinc, and these are often available as waste products. So it could be possible. The problem is how to change the clinker formation.
And whether the size of this, what kind of, suppose zinc is in a powder form, so size will matter?
Well, no, I mean, basically everything has to be dissolved in the high temperature reaction. So it has to go into solid solution in the halide. We were originally going to look at a lot of other elements, but then we realized zinc was kind of unique because it's not really very toxic. It's actually important for human health. You take zinc tablets if you have a cold, and it's relatively abundant. So, you have quite a lot of zinc around, so it's not totally impractical. Almost everything else is either toxic or very low abundance, so it would make something very expensive.
Thank you. Thank you.
Good afternoon, Professor Karen. I was really overwhelmed the addition of zinc, how it is changing the CSHL properties. Now, when we look into the doping of zinc, there are two routes, as you explained, through clinker and through solution as we are adding chemical additives. Now, have you ever seen what are the difference in the impact when zinc is doped in the clinker or when the zinc is added while cement is under hydration?
It's totally different. If you add it separately, it gives a massive retardation. This is actually well known because it's very difficult to immobilize waste which contains zinc. If you have zinc in solid, zinc oxide or something like that, then you retard the reaction for days, if not weeks. So it's very important that you have these very low dosages, and the zinc is dissolved in the C3S, so it's only released a little bit at a time.
And in case zinc is taken in form of a solution, along with the,
it goes into solution and then gets incorporated in the CSH, as we could see by the NMR work.
What would be the recommended doses? Have you ever tried when it is added into the cement itself?
Sorry, I didn't hear.
Recommended doses of zinc solution.
Yeah, it's not. We have a dosage of about 1 or 2% in the halide phase. So the dosage in solution, you really can't measure it because it's very, very low.
So thank you very much.
Thank you.
Thank you, Dr. Pandey. I think we'll take one more question from the audience, a very quick one. There's somebody in the middle over there.
There's somebody at the back.
I hope it's a quick question. Okay, two of them are going to ask questions at the same time. Let's see who's louder.
Hello. Good afternoon, Professor Karen. I wanted to ask, if this zinc is actually forming a nucleation particle around which the CSH is forming, or is it something different?
No, it's actually getting incorporated into the CSH phase. You can read the art. You should go and read the article. It's all really explained there.
Okay.
Thank you.
Okay, one question other than zinc.
Yeah, exactly. I didn't only speak about that.
Dr. Chatterjee, please. We'll give Dr. Chatterjee a chance.
These days we are trying out the seeding technology for hydration purposes, and what's your view on that? in the context of all the new revelations?
Yeah, that's a very good question. We did actually look quite a lot at seeding technologies. And it's, first of all, I say it's quite difficult to decouple the intrinsic effect of seeding from the fact that these seeds are often stabilized by alkali. So we know that if we put alkalis in our cement, we get an initial acceleration, but then in the long term, we get a strength development which is not so good. And we tend to see the same with seeding. We tend to see an initial enhancement, but at long-term ages, like 28 days, the strength is not so good. Now, the people who are making these seeds are trying to overcome these problems, but at the minute, we see that the impact of seeds is relatively low, and the products that are available on the market are quite expensive. So they could make sense for somebody like precast manufacturers, but I don't think they make sense in bulk concrete. It's a little bit complex and rather expensive. But of course, this is an approach we want to keep in mind. It may help us understand the puzzle of really what's happening. I should incidentally say that it underlines the importance of really well mixing your concrete. Because if you really mix well your concrete, you actually create your own seeds, because you have this very fast nucleation of CSH. And if you're mixing well, you really distribute those seeds through the volume, and you get a much better microstructure afterwards.
Well, thank you, Professor Scrivener. I think we'll have to end the discussion here. I thank a lot the audience as well who asked a really interesting question. Let's have a big hand for Professor Scrivener. Next, I would like to introduce Professor Thomas Matschei from RWTH Aachen in Germany. He's another person I've known for a long time, probably around 20 years, and he has a lot of experience in the industry as well. He worked in the R&D group of Holcim after his PhD that he did at Aberdeen in Scotland. After that, he went back to Germany and has been a professor there since. He's been at Aachen since the year 2020, and we've been working quite a lot together as well, so we are hoping he's going to be a regular visitor to India as well in the future. He's going to talk about binding the future from calcined clays to extrusion. Thomas?
Yes. Thank you very much, Shashank, for the kind introduction, and thanks to the organizers for inviting me here. It's a pleasure to be here back in India, and as Shashank said, during my active time in Holcim, I was a couple of times also here and helped our colleagues here. The topic of my talk today is a little bit different from Karen's, so I move one step up because I would want to look a little bit more at the interface between the cement and the concrete. And since I'm working in a civil engineering faculty, I'm focusing a lot on using hydration as a tool, but at the end of the day, we want to make, with that tool, the concrete better. And that's why I try to give you some perspectives how we can do that. At the outset of my talk, I'd like to sort of look back of what has happened over the last years. And over the last years, what we had seen basically in a cement world, but also in the concrete world, we've seen that we have a lot of promises given. And we have a lot of promises given how we're going to reach carbon neutrality, we want to reduce CO2. But unfortunately, if we're looking into true reality until today, not so much has actually happened. The slide that I'm showing you here is actually, and it's not only true in the developing world, it's also true in the Western world, for example. The slide I'm showing here is an example from Germany. And what you see here is, on the columns, is the evolution of the CO2 emissions. And if you look into the evolution of the CO2 emissions, you would think that basically 2021 was a breakthrough, because suddenly we realized that there is CO2 starting to go down. And 2023 had quite a lot of lower CO2 emissions in the cement world. Unfortunately, what happened actually at the moment in Germany is not that the CO2 goes down, but the cement production goes down. And this cement production that goes down at the end of the day has, as a conclusion, much lower CO2 emissions. But if you're looking actually into the specific CO2 emissions per ton of cement, basically, I think since 2005, we didn't make much progress. So really, we have still a clinker factor which is on the order of 0.7 there, and we need to move on, and we need to move on worldwide. But if you're looking also globally, we also see for the moment not so much happening. A part that we see globally also sometimes in a few countries such as China, we see a decrease in CO2, but mainly also due to a decrease in production. If you're looking to India, we see the opposite. For the moment, you're still in a massive increase, so that's why I say it's not India here. But also, I think in India it's the same story. We have kind of a stagnation if you're looking into the tons of CO2 per ton of cement. So, and therefore, we need to do something, and we need to come up and develop solutions for that. And a few solutions I'm going to show you are basically included in my talk here. The other message that I would like to give is, if we're thinking about cement and we're doing cement production, we also have to think about how we're going to use the cement later in the application. And with that, I want to say produce cement, but think concrete. And here, I think just a few weeks ago, I think the Global Cement and Concrete Association, they introduced an interesting scheme, which basically gives you kind of some CO2 efficiency classes for concrete. And we see that we need to come down with the CO2 emissions, not just per cement, but also per concrete. So we need to act at the same time at different levels. So we have to work on the cement, but also on the concrete, and we should not forget about the concrete at the end of the day, because this is the material where the cement is applied to. And if you're thinking about the concrete, we also have to think about on which concrete we have to basically put all our efforts in. And it's not so much the high-performance concrete on which we have to put a lot of effort. That's still a niche, more or less. But what we have to do is basically looking into the normal strength classes that we have. And on that graph here, you see this is a famous Daminelli curve from 2010. You see that is actually the most tricky part to decarbonize the concrete, which we use most of the time on the planet. But this is actually the concrete on which we have to focus for, because this is at the end of the day giving us an economical advantage and an ecological advantage at the same time. And this is something which we need to do now. And if we want to achieve that, we have a couple of pillars which we can influence all that we are here in the room. And the main pillars of decarbonization that I just summarized, which are also a conclusion of all those roadmaps, are 4 of them. First of all, we have to reduce the CO2 and the binder and the cement. We can also use alternative clinkers, but we also have to use low-carbon concrete materials. At the second time, we also have to look back, how can we exploit circular economy measures? So we have lots of waste materials out there, lots of byproducts that are actually harmful to the planet, and we should look for solutions to use them and to bring them back into the construction cycle. And the third point I want to make, and this is something I would like to end in my talk and bring back to that, we also have to look back into the application and talk to the structural engineers. And first of all, we need to educate the structural engineers that we have done a lot of progress on our fields on the material side, and we need to bring that progress then also into the structures that are all around us. And this is, I think, key focus also for the future, that we need to integrate all the actors of a cement and concrete value chain, because otherwise I don't think we can achieve our climate neutrality targets. And in there we have to basically leverage all aspects of modern concrete technology, but at the same time we have to be open for new production technologies, new reinforcement concepts, etc. And the final part, which was covered today in the morning session, which I attended, I will not go too much into detail in that presentation, but it's another important subject that we also tackle at our school, we have to look also into CO2 not as a waste, but maybe also as a chance, and try to use as much as possible as a raw material in order to enhance CO2 utilization measures also into concrete. But let's start and move back a bit to the binder level. And I would like to bring a few examples on which we were working on, and a few of them you know very well. And the first one that you know very well is the use of calcined clay and limestone. If you're looking into binders, I mean, this combination is deemed to be successful because it consists of two materials that are typically widely abundant on the planet. So we have limestone, which is a base material for our cement. We have lots of quarries of that. And we have clays that can be later calcined or activated that we can then bring together to make a useful binder out of it. And I think this has been said in numerous talks over the last 10 years. I just want to remind you why it's such a great combination. Because what we have in order to come up with a very nice binder is we have the calcium carbonate or the calcite from the limestone, we have the calcium hydroxide that's coming from cement hydration, and we have reactive alumina and silica that's coming from the activated clays. And if they are coming together in solution, they're forming very important hydrates. One of them you heard in the morning, which is the CSH, which also includes a bit of aluminium, for example. And another hydrate that is quite important in this binder is AFM phase or the carboaluminate phase. And here we have the synergies where we see we're going to get the alumina from the clays, and it reacts with the carbonate and the calcium from the cement and forms additional hydrates. And these additional hydrates, they contribute to space filling, and at the end of the day we're going to get a higher strength, and we're going to get strength synergies, especially if you're using the products limestone and calcined clay in combination. So now we have to also think how to start to produce those cements. And as I said, we need to come to action. And one thing that is important that we want to bring to the industry is actually tools and know-how to optimize those binders. And this is something that we do actually together in collaboration also with IIT in Delhi, and Shashank and Menas, who's here in the audience. We want to come up with tools that help the cement producers to obtain a fundamental understanding for a well-controlled and optimized production of cements containing calcined clay and limestones. And these tools should be potentially rather simple to use. And if you're looking into the performance of these calcined clay limestone cements, what we typically see is that we have different raw materials, different clays, and these different clays, they can look completely different and have also a huge impact on the performance of the resulting binder. And what we have understood, I think, quite well is the relation to the long-term properties, saying the strength at late ages, 28 days, 90 days, is mainly a function of the metakaolin content, and therefore a lot of people actually focused on looking at kaolin as a main quality parameter for a good clay. But if you're looking at the early age of those early age properties of those calcined clay limestone cement, you're going to get huge differences. And what we realize quickly is kaolin is not really much the determining parameter. So we have to look outside the box. We have to think different, and we have to think about other parameters and not just looking into metakaolin. And this was also the starting point of our work. The same is basically true if you're looking into workability issues, and we know that some of those clays, they can cause huge workability issues in the field. That starts with high superplasticizer demand, so the concrete becomes sticky, and one clay again is different than the other one. Or what we also see quite often, we're going to have a good mix that leaves the concrete plant, but then after 20, 30 minutes, we have a lot of stiffening, and the clay is not really able to be placed anymore. And then, of course, there's a risk of water addition, which we all not intending to do on the construction side and not wanting to do. So now we want to understand, want to come up with test methods how to better understand all these properties that are related to early ages. And one thing that we had now come up with is actually something that was inspired, I think, from India, because we look a little bit into a sophisticated version of your lime reactivity test. And what we are doing in our program here is we use basically clay as an intrinsic or as a single component, and we separate it from the clinker. And we activate that clay during hydration by adding calcium hydroxide, calcium sulfate, and maybe a bit of limestone to it. And then we're going to see how it's been reacting. And this is what we had done, and we had looked into how this clay reacts, and we come up with a very distinct reaction pattern of this calcined clay. As I said, it's a very simple test that everybody can do. And if you look into a calorimetric fingerprint of this calcined clay, when you add calcium hydroxide and calcium sulfate, you're going to see a curve which is like this. And this curve is relatively easy to be explained because what we're seeing at the beginning is we see a lot of heat that's been released. Then suddenly we reach a plateau. This is when the yttringite and the calcium silicate hydrate precipitate. And at one point, we're going to see an additional heat increase. And this is intrinsic because at that point, the sulfate has been depleted and has all fully been consumed. And if you're adding all the time the same amount of sulfate, that sulfate depletion peak is very nice because it gives us a very simple tool and a simple measure that we can benchmark the clay reactivity of each different source, and we can bring that back into relation to our practical performance, especially at early ages, and that works quite well. And what we saw then finally is that we have the clays that have the highest iron content. They have also highest specific surface area, and not surprising, at the end, they give you a highest reactivity. And this is now something that producers can take away, and you can basically benchmark clay versus clay in your laboratories, given if you have, for example, devices such as colorimetry. You can do the same also with conductivity, so there's not big differences. What is also very interesting is that, of course, this early reactivity is connected to a precipitation of hydrates. And the hydrates that are forming at very early ages, typically in those clay systems that are yttringite, but also to some extent CSH. And if we're getting a lot of hydrates forming, we also have potentially an impact on the rheological properties. And I was saying at the beginning, workability properties are typically one of the main issues with calcined clay cements. And if you're now investigating the rheological properties of these simple calcined clay pastes, we see a very nice relation between the clays that have the highest reactivity also to the clays that shows the fastest stiffening. So in there we have now a tool actually to master basically the clay constitution. And finally what we can do in the next step, we can link that all back to properties such as early strength, at the same time also superplasticizer demand. And what we see is something that you have to watch out in the field is, first of all, check whether the clays have a high iron content. Then it's worth to look into a specific surface area measurements, for example, by PET. And then you need to see how does that basically impact reactivity and superplasticizer demand. And you see here, this works relatively well. And what we have seen so far is that most of the clays that have very high iron contents, they are also the most problematic ones in terms of workability. At the same time, they're giving you high reactivity, so it's quite beneficial for the strength. So you need to see at the end of the day for what purpose you're optimizing your cement for. Good. But we have not only calcined clays, we have also a lot of other materials on the planet that are relatively abundantly available. And our colleague Ruben Snellings at the last IICC in Thailand, he made a nice collection of all the so-called emerging SCMs that we have available, and he put that all in a diagram, as been shown here. And one of them, which is very interesting, is, for example, the so-called steel slags or BOF slags. We have around about 200 to 300 million tons per year available on the planet, which comes from the crude steel production. And what is interesting, if you're looking into this BOF slags, it contains quite a few of the minerals that are also potentially interesting for cement hydration. The most important one is belite, but beside belite we also have ferrite in it, and we also have a bit of calcium oxide in it. So we have more than half of its constituents of this BOF slug that can actually contribute to some of the hydration products. What is, however, quite critical in all those emerging SCMs is something that's highlighted here. So they are typically quite iron-rich. And this is something that was not so much focused on in the hydration literature over the last 10, 20 years, because always this iron and cement was always kind of a miracle. So where does the iron go? And we still don't have a full understanding until today of it, because some people say it's going into ettringite, some people say it's going into AFM phases, others say it goes into hydrogonate, and we need to study that more. And this is something where I don't have a solution as of today, but what we clearly see is if you're applying these high iron-rich SCMs into application, we see totally different hydration products, which were typically not so much forming in our Portland cements. One of them is shown here. This is a study that we had done on basically a carbonation-activated steel slag. So by that we got a bit higher reactivity at early ages because we had precipitated quite a bit of amorphous silicates and aluminates. But we also had quite a high fraction of ferrite remaining. And if you look into the hydration of this system, we suddenly see a lot of what we call silicious hydrogonate forming all around these ferrite particles. And that is something that we always claimed in the past, but in normal cements we don't really see that. And now what we need to do in the next step, we have to understand better what's the impact of this hydrogonate formation. Is it something good? Normally it's quite a stable phase, but we have to study that now by thermodynamics in order to also now develop new models that are applicable to these iron-rich cements. And then this is something where we're still lacking, and that's something we need to do now as a next step. Another interesting material that's out there, and it's very harmful and toxic to us as human beings, is red mud. I mean, currently we're producing around about 180 million tons per year. The trouble is, so far, we didn't use anything of it. So on the planet, we have more than 4 billion tons of this material accumulated in deposits that look like that. They are huge kind of lakes, and we just had in Hungary and in South America cases where the dams broke and quite a lot of people killed, and it's very toxic to the environment. So it is of extreme importance that we utilize basically that material, and since such a high amount of that material is available, it speaks for itself that we can probably, or we should probably do something and use it as cementitious material. And this is what we had done actually together with our colleagues from Holcim in a project called Reactive. There are 7 aluminum producers put their heads together with a cement company, and we try to understand if you beneficiate that red mud by thermal chemical processing, how can we make a better cement out of that? And this is what is interesting in there is that, again, here we're going to get very interesting materials that we didn't know before. So we're going to have very nice or very interesting materials that contain very strange phases. And one of these strange phases that we have in there is so-called concrinite or sodalite, that basically we had no idea how they are reacting. So what we are now trying to do, or what we have done now, is we've synthesized these materials and looked into the material, how does it react, and does it actually contribute chemically to hydration. And this concrinite is quite interesting, or the sodalite. If you're looking into it, it has actually pozzolanic properties. And this is shown here with help of a thermodynamic simulation that we had done. So if we are adding calcium hydroxide to the sodalite, we see we're going to form CSH, again a bit of stratlingite, and maybe again the silicious hydrogonate. But these are phase assemblages that so far they were maybe sometimes observed in calcined clay cements, but not in relation with these concrinite. As a consequence, if we're looking into cement hydration and we put the materials into cement, what we also see there is suddenly we're going to get completely new phases in there. We have unknown AFM phases. These are these platy minerals. And And these AFM structures, they are kind of the waste bin of cement hydrate. So a lot of materials try to intercalate in a layered structure. And unfortunately, or fortunately enough, we have understood it very well for systems such as limestone and calcined clay. But unfortunately, we haven't fully understood it for these new systems. So therefore, also here, we need to do way more studies and to understand that a bit more in detail. So now I want to move on in the last part to give a bit of perspectives. I want to move on and said, as I said at the beginning, we need to think concrete, and we want to use these binders, which are shown to be very complex, also later on in construction. But if you're looking into construction, also our colleagues from the structural concrete departments, and I'm always at the interface between both, they're also quite active at the same time to come down with the carbon footprint, but they're not looking too much on the binder level, but they're going way more on the structural level or even into the element level. And one thing they focus at the moment, or we focus at the moment together with them, is actually looking into the, specific CO2 emissions per building. And if you do that, what you see and quickly realize is that most of the CO2 in a building is basically in the slab. And therefore, what we are doing at the moment also, beside binder optimization, we're looking into new construction principles for optimized slab designs, where we try to use or try to minimize the binder that we talked about earlier. And now also in the next step, we want to include these environmentally friendly binders into construction. Why slabs? I mean, slabs simply do have the highest specific CO2 emissions that are coming from the material in a building, and therefore it is very, very clear that one should focus on one thing first, and therefore it makes much sense to just focus on the slabs at the very beginning. And if you want to further decarbonate those CO2 footprints on the slabs, you need to come up with new construction principles. And here we have a very interesting project. It's together with the University in Dresden. It's a so-called collaborative research center where we have 26 PhDs working on new design principles, not just for slabs, but slabs as a main component of that. And in there, we're looking into nature-inspired structural designs, but we also look outside the box, and that's quite fun because we also look into mathematics. So we work together with the mathematical people in order to see how we can create structures that are self-interlocking. And we even look into origami-inspired designs from Japan. And you may think this is a bit crazy, but it's actually quite interesting because what the Japanese have found is they have a so-called water bomb concept developed with origami. Basically, it goes back to if you fold a paper structure as such that it can hold as much water as possible, then you have a structurally optimized paper design because you can basically stand on it, walk on it. And we are trying to adopt this origami-based design and also into construction. And if you're looking into nature, one thing that inspired us, and this is quite efficient, is if you're looking into bees. And this honeycomb structures that we have here is very efficient because it's very stable, and at the same time, the bees, they also don't want to waste their energy. They want to come up with material efficient designs. So we took that as an example in order to also develop a slab concept out of that. And one thing that we have in our institute is something unique because we have, and that's now I'm coming to the extrusion bit of the talk, we have a so-called concrete extruder that was standing in our lab since 10 or 15 years. And at one point we thought, why don't we dig it out and do something useful with it in the frame of that project? And we created a mouthpiece with that extruder, and in that mouthpiece, and it's shown here, we have now the opportunity, and this is in contrast to all the 3D printing methods, we can integrate reinforcement. And this is a big problem that the 3D printing community has that we have overcome, because we can use alternative reinforcement based on carbon or even glass, would be better because it's much cheaper, and then make structural elements out of it, and we can produce them relatively cheap in a serial way, as you can see here on that picture. And this is our laboratory extruder that we have in Aachen. And what you also see in that laboratory extruder, we can basically adjust the dimensions of that extruder. make it thin and less thin. And this is important because we want to later integrate that back into a slab design. And then if you're optimizing the rheology of that mix to such an extent that, as you can see here, what the students do, they have actually, by the way, a lot of fun to do that, and that's a huge boost in the student numbers that we got into our institute, because they're all very interested in that. They basically can shape that material later on, and we can start to create structures out of that, as you can see here. And we let that harden. We, of course, have to cure it. We can even induce carbonation curing in order to speed up the hardening. And we can, at some point then, and as it will be shown in the next slide, we can now integrate it back into slab design. And we can come up with this honeycomb structure that we had shown before. And finally, you see here this waved structure. This is quite good because we can bind it to the concrete that's been there, and we can cast it from two sides. And at the end, we're going to have a slab that has about 60-70% less concrete, but has the same performance in terms of structural application. And you see here a lucky student of us. And so this is kind of a first example that I want to show you how we can integrate structural design also into material minimization. Another example that I would like to show you is this origami-inspired one, and this is the one with which I will close. This is this water bomb shells I was saying before. They're interesting because they are basically giving you the highest load-bearing capacity for the lowest amount of material. And we just recently, as you've seen here on that picture, had a fun workshop with some people that are working on origami together in Dresden in order to also attract the students to it. But what we wanted to do out of that, we wanted to also make something useful out of it, and we collaborated with the mathematicians. And by collaborating with the mathematicians, we created modules that we can produce by folding concrete. As you can see here, again, it's quite a challenge on the rheological side, but it can be done. And by creating these modules together, we can work together with the mathematicians and come up with a slab concept where we interlock those modules mathematically, and then they don't move anymore. And finally, if you put a frame around it, you can standard it in this load bearing. And you can put, at the end of the day, these materials on any truck, and you can just, like a Lego or puzzle, you can create your ceilings, and then you have like a mini ceiling concept. You pour some concrete over it, and then you have, again, a material minimized structure. So this brings me basically to the end of my talk, and I hope I've given you a bit of inspiration how we should see it in the future. So I think what is important is that we think about cement and how to improve cement, and it's very important that we work on very fundamental aspects, as Karen was showing before on the CSH side. But at the same time, we also need to think about the application. And we need to also get a message across to the students that it is important to work on both sides. And therefore, I want to make a pledge basically to the students, but also to the industry, that we need to move towards, I would say, a chemistry-informed civil engineering community, because what I've seen now in the field very much, and when I talk to structural concrete people, they don't know anything about what is ongoing in the world of our materials world. So they basically know, if you think about low-carbon cements, they only know geopolymers, they don't know about all these other systems. But in the meantime, they also know calcined clay cements, but they have no clue about the rest. And I think it's our duty that we start already with the education of those students in order to bring chemical aspects into the curriculum of civil engineering, and also try to lift that together. And then we need upscaling methods, probabilistic approaches that are linked to AI approaches, and finally with that we are able to optimize structural elements starting from the binder design. So thank you very much. This was my pledge, and thanks for having me here.
Thank you, Thomas, for a very interesting talk, and let's have a few questions from the audience before we move forward. Are there any questions? Please raise your hand if you have. There's one behind you, Dr. Chatterjee, and after that we'll come to Dr.
Good afternoon,
Chatterjee.
sir. Myself, Yashobhoomi Ahmed from NCCBM. I just have one query regarding the red mass based cement system as you have shown. There is a problem related to the alkali in the red mud. If we are using it in the cement in terms of after calcination or pre-calcination, and we are again saying for the alkali silicate reaction for the concrete, is that issue can be overcome if we are adding more red mud in the cementitious system?
Can you quickly repeat? I didn't fully understand.
There's a bit of an echo, so if you can speak a bit
it's an echo, yeah.
I mean, in red mud, as we know, there is the alkali content is little higher side, and we are making cement from that, so the cement will having also.
He's asking about the issue of alkalis in red mud.
Yes, the issue of alkalis in red mud. Yeah. So this is a very important question, and I think this is something that we have to tackle. So there is ways how to to take out the alkalis, but if we have the alkalis in the system, what we also see is we can use them to some extent to activate part of the cement. That's working relatively okay. But of course we need to be careful with some durability aspects, and this is something we're studying here, which is, for example, related to a problem of alkali-silica reaction. But what we actually realize is, what we realize, what is important is that we need to process the material. So we cannot just take it, dig it out, and throw it into cement. I mean, that doesn't work. I mean, first of all, we have all the heavy metals and the toxic elements in it, and secondly, the reactivity is rather minor. So what we were trying to do in that project is, for example, we co-calcine it with clays, but also we look into vitrification methods, and then we're going to get quite a huge boost in the reactivity, and then we can make, again, a ternary blend out of it because we can combine it nicely with limestone. We can take advantage of the reactive alumina and the iron, and then come up with, again, a relatively well-functioning binder system. But you're right. I mean, we need to watch for the alkalis. But to some extent, they're beneficial because they're also activating our clinker component. So at the end of the day, it's not too bad. But we have to put a warning in for ASR.
Thank you, sir.
Thank you. There's a question from Dr. Chatterjee in the front.
Just two small things for you to give us a perspective. One is, what is the status of the steel slag usage in the cement manufacture? Because this is a crying problem for last maybe 4 decades, and very little progress. In our country also, very little progress has really taken place regarding the use of the steel slag. So is there any jump in the usage elsewhere, or what is the global status of real use of the steel slag in the manufacture? That's one part of the question. The other is about the ultra high performance concrete and avoiding the steel rebars and using only the non-metal fabrics. There are quite a few things, and few structures have already been done. They appear to be quite promising, but I would like to hear from you that in the context of the present climate crisis and things of that kind, is this the right approach to follow?
Yeah, thanks for this question. I think two very relevant remarks. So coming to the steel slags, I think we have we had that always on the list, I think, of materials, also from a cement production point of view. I mean, since my time already, because we had a shortage of normal slags. What is still a problem in there is if you're having lots of iron in it, so we're going to have huge wear in the mills. And this is something that we need to tackle, so we have to come up with a good separation procedure in order to get the metallic iron out, because otherwise it may cause a huge wear. And that means we have to invest also into processing of those steel slags. And the second thing that is actually something that we are now targeting as well, but it's related to at least for some of the slags, we have, for example, quite a bit of chromium in it and quite a bit of heavy metals in it that we need to watch. And then we have a couple of countries, for example, Germany is one of them, where we currently are not allowed to use, for example, steel slags, because what people do is they look just at the solid contents of the impurities, and then they put them already on the red list. And what we do is we use it as a road filler, and we put it to landfill. And I think this cannot be. So I think it's such a nice, good material, and as we have seen now, and there's a lot of research now going on, at least on Europe, how to activate those materials, be it chemically, be it with CO2, in order to make something useful out of it. And what we also see now is, if you're looking into concrete as a binding matrix, so we have lots of CSH which interacts with these impurities as well. I mean, it has a huge surface, it binds it, so at the end we don't see huge problems in terms of leaching. We need to somehow take care of issues such as chromium, but this can be all done. So we have to, at the end, engineer our binder in order to kind of don't leach out these materials, and we have to process them in order to come to an acceptable wear of our machinery, because otherwise it's going to be expensive and people will refrain from using it. So this is two things that we have to tackle. So the second question on alternative reinforcement is very relevant. I mean, when I came to Aachen, I thought, yeah, well, why is that any useful? I mean, look, I came as a civil engineer, we're doing steel. But there was a lot of research ongoing over the last 20 years on alternative reinforcement, and then at one point it made click in my head, and I said, wait a minute, it's brilliant, because now we can use a material where we don't have to bother about carbonation anymore. We can even enforce carbonation and bring the alkalinity down. The reinforcement doesn't care, it actually likes it. For the moment, we do quite a bit of research on carbon reinforcement. It's quite expensive. But what we are trying to do, and this is something we'll look into it in the future, is also going back to basalt fibers, glass fibers, but then looking into fully carbonated systems, and then hopefully come up with a much better utilization of the concrete itself and of the reinforcement. So this is something where we look together again with the structural engineers, and this is working very well with the low carbon binders. And yes, we don't have to go to ultra high performance concrete. We may have to go to 50, 60 MPa, but we are still on the lower side of the concrete. I would not necessarily want to go to ultra high performance concrete, because it's what we see already. To the examples I had shown, we are maybe about 50 MPa. But we have to work also on the carbon footprint of those those elements and bring them down. And this is ongoing research at the moment.
Thank you so much, Thomas. I think we've heard two very interesting talks today, but first let's give a big hand to Professor Thomas Matschei. We've heard two very interesting talks today about various approaches we can use to reduce CO2 emissions. We'll close this session over here, but before we close this session, there are a few things. Maybe you can take a seat again. Before we go into the presenting the mementos part to the speakers, there are a couple of things we have to announce. First, after lunch, there will be a session on cement chemistry over here. I request the audience to come back. I hope this will be very interesting. Second, I'm also very happy to inform you that NCB is signing MOUs with two organizations, and we will have that signing of MOUs right after the session, so don't leave this room. Stay here for a few more minutes. We'll make sure that there is still some lunch when we get there. NCB will be signing an MOU with GCCA India and also with Institute of Plasma Research right after this session. So once again, a big hand for the speakers. And we give back to the MC of the session.
Yeah, thank you very much, Vishnoy sir. And thank you very much, speakers, Professor Karen and Professor Thomas, to sharing your research with a different topic, but the aim is same, decarbonizing the industry. So now I request chairman of the session to present a memento to our renowned speakers. Now I request Dr. S.K. Chaturvedi, please give a memento to our chairman for conducting this session so smoothly and within the time. Thank you very much. I request one group photo. Now I request with the speakers, we can have a group photo here.